So questions 1 and 2 are all about the properties of exponents. You couldn't do this problem if you didn't know the properties. Here are the main ones that we talked about. There's the product property, which states if you are multiplying two exponential expressions that have the same base, you can condense it together as long as you add the exponents. The quotient property says the exact opposite. If you're dividing like bases, you can condense them together as long as you subtract the exponents. The power property states if you have an exponential expression and you raise it to another exponent, you go ahead and multiply the exponents. And the last of the main ones that we typically use is the negative exponent property, which says if your exponential expression has a negative exponent, all that negative exponent tells you is to reciprocate the base in order to make the exponent positive. So there are a lot of avenues, a lot of pathways you can take when you're simplifying these expressions. This is simply one way that I'm going to take. First thing I notice is we have an exponent outside a set of parentheses. That usually tells you to use the power property and distribute the exponent of 2 in. Distribution is multiplication. So anything that's not highlighted, I'm just going to copy down my next line. So applying the power property, we get x to the 10th, y to the 6th times, and then just copy the rest of the problem. Next, the path that I'm going to choose is I'm going to try to clean up the numerator. Notice everything in the numerator, they're just multiplying each other, so it's the product property. Do note that these properties of exponents only work for like bases. That means you don't want to mix up the variables, only look the variables together. So you work the x's with the x's, work the y's with the y's, and at least in the numerator, the z's by itself. So anything that's not highlighted, I'm just going to copy down. So the product property states when I multiply, I'm going to add the exponents. So for the x's, that's x to the 10 plus 3, which is 13, and y to the 6 plus negative 5, which just is 1. And then I'm going to copy down the rest of the problem. Now that I've simplified the numerator and denominator as much as possible, I can look at the whole fraction. That's the quotient property, the division property. And the division property states if you divide like bases, you subtract the exponents. And again, you only look for you only apply the properties to the same variables. You don't mix the variables. So for the yellow, the x's, 13 minus 4 is x to the 9. Now take a look at the quotient property. The quotient property says a minus b, the numerator minus the denominator, and that's technically true. What I like to do instead is big minus small. I just have to remember if I'm going to do big minus small to put my answer wherever the bigger exponent was. For example, in the y's case, we have y cubed is the bigger exponent, so I'm going to do 3 minus 1, which is 2. But I'm going to put the y squared in the denominator because that's where the bigger exponent was. Same thing with the z's. The bigger number is 5, and I'm going to subtract the smaller number of negative 3, which gives me 8. But I'm going to put the answer, z to the 8, in the denominator because that's where the bigger exponent was. This is the simplified form for number 1. Number 2 works the same concept. The only difference is you might be dealing with fractional exponents. And I'm sorry to say there is no way around it. You have to be proficient with fractions, be it mental math or with a calculator. We can't run away from fractions. So the first thing I notice is exponents outside of parentheses. So I'll go ahead and apply the power property and distribute those exponents. Again, anything that's not highlighted, I'm just going to copy down. So distributing this exponent of 4 thirds, again, I'm just multiplying fractions. If you don't know how to deal with fractions, again, just use a calculator. That's m to the 16 ninths, n to the negative 16 ninths, and p to the negative 4 thirds over distributing this 4 thirds gives me n to the 4 thirds, m to the 1, so I'm not bothering writing it, and p to the negative, negative 2? Negative 2. And then bring down the m to the 3/4, n to the 3/2, p to the 1/4. Next, what I'm going to do is clean up the denominator because there's a whole bunch of terms multiplying each other. So again, you only do the variables that match. So the n's with the n's, the m's with the m's, and the p's with the p's. The numerator, I'm not going to do anything, so I'm just going to copy down my next line. M to the 16 over 9, n to the negative 16 over 9, p to the negative 4/3 over, and I'm just going to go alphabetical order, so do the m's first. So m to the 1 times m to the 3/4. You add the exponents, 1 plus 3/4 is 7/4. Do the n's, 4/3 plus 3/2 gives you 17/6. And then the p's, p to the negative 2 plus 1/4 is negative 7/4. And now you go ahead and do the quotient property. So do the m's together. Do the n's together. Do the p's together. So when you subtract these exponents, 16/4 minus 7/4, that gives you 9/4, m to the 9/4. I'm going to do 17/6 minus a negative 16 over 9. So I'm doing big minus small. So 17/6 minus a negative 16/9 gives me a 83rd 18th on the bottom. And let's just say for the p's, okay, I don't know which one is bigger. Is negative 4/3 bigger? Is negative 7/4 bigger? I don't know. So if you just do top minus bottom, negative 4/3 minus negative 7/4, the rule of thumb is whatever you start with, that's where your answer should go. So negative 4/3 minus a negative 7/4 gives me a positive answer. Hey, I lucked out. So that gives you a positive 5/12. So the p to the 5/12 should go on top. So that should be the answer to number 2. Same properties, just with fractions. Number 3, 4, 5 is all about rationalizing specifically the denominator. The idea is a square root and a square are opposites of each other. A cube root and a cube is opposite of each other, so on and so forth. So an nth root and an nth power are opposite of each other. So you have to do whatever you need to do to get those exponents in. So in this case, to rationalize, all I care about is getting rid of that radical 5. So I need an exponent of 2. An exponent of 2 means multiply by itself. So I'm literally going to multiply by radical 5. But of course, what you do to the numerator, or excuse me, to the denominator, you have to go ahead and do to the numerator. So this equals, go ahead and distribute, 7 plus 9 root 50 over, now the whole point of multiplying by itself, this guy here, is you should know that that equals just a regular 5 because the square root will cancel. So in the denominator, we have 10 times 5, which is 50. Now the instructions did say simplify as much as possible, and we should recall, we should know that root 50 is the same thing as radical 25 times 2, and radical 25 is 5 rad 2. So this right here will get substituted for the radical 50. Notice the 9 is not highlighted, so when I write down my next line, I keep the 9 there, substitute the 5 rad 2, and then go ahead and multiply. 9 times 5 is 45. When it comes to simplifying fractions with radicals, you have to be able to simplify all of the coefficients. So if this was simplifiable, I would ask myself, is there anything that I can divide out from a 7 and 45 and 50 at the same time? The answer is no. So this is as simplified as possible. Number 4 is the same concept, except it's a cube root instead of a square root. And again, The opposite of a cube root is an exponent of 3. An exponent of 3 means I need 3 factors. Well, in this case here, I currently have just a regular 5. We have a 5. We want 5 cubed, right? Which is just 5 times 5 times 5. I hope it's very obvious to everyone that we need 2 more 5s, or in other words, we need a 5 squared. So I'm going to multiply the denominator by the cube root of 5 squared, but what do you do to the bottom? You do to the top. So this equals 5 times the cube root of 5 squared, which is 25, all over. And again, the whole purpose of doing this multiplication is that you're going to get a 5 cubed inside of a cube root, so they cancel out, and to give you a regular 5. Again, to simplify fractions with radicals, you only have to look at the outside numbers, and clearly 5 and 5 will reduce, so the answer is just simply the cube root of 25. Number 5, you have a square root in a binomial. And the idea is, in order to square individual terms within a binomial, we're going to exploit the following pattern. The pattern is, if you multiply two conjugates, a minus b, a plus b, that will always equal to the first term squared minus the second term squared. This is the only way you can square individual terms in the binomial. If you just flat out square a binomial, you're going to be left with a middle term, and this is the term that we do not want, so that's why we don't use this pattern. We use the conjugates instead. So that's the technique. Just multiply the numerator and denominator by the conjugate of whatever it is you're trying to rationalize. Go ahead and distribute. So that's 6 plus 2 rad 10s over, and we don't have to do all the foiling in the bottom because we know the pattern. This is the pattern right here. So we know that the product of two conjugates is the first term squared, 3 squared is 9, minus the second term squared, radical 10 squared is just a regular 10. That's why we do it, so we can break down the square roots. Just go ahead and do the math. And you should know that dividing out a negative 1 is the same thing as flipping all of the signs. Number 6 and beyond is just straightforward factoring. I hate to say this, there is no special technique, there is no special trick to factoring. It's one of those, you have to know it, or if you don't know it. So if by now you still don't know how to factorize, that should be on your to-do list. Ask me, I can give you a bunch of practice. We can get this. But there is a thought process that I like to take. If a quadratic trinomial is factorable, we know it's going to be the product of two linear factors. Whatever I put in the first positions has to multiply to the first term. Now, since it's just an n squared, that's easy. It's no guesswork, really. It's just n times n. Whatever I put into the last positions here has to multiply to the constant term, the last term here. And once you fill in these numbers, you just have to do a quick multiplication, quick FOIL, to make sure it syncs up with the middle term. The way I like to do it is I like to take the last number, 6, pairwise factor it. What two numbers times together equals 6? Start with 1 in the number. 1 times 6 would work. 2 times 3. This last symbol will tell you to think add or subtract. In this case, since it's a minus, I'm going to think of subtraction. This is what I'm thinking. What pair subtracts to the middle number? And in this case, the middle number here is just a 1. And this was a pretty simple example, but I hope everyone understands that 2 and 3 subtract 2 and 1. The order in which you put these, it doesn't really matter. Now you have to figure out the pluses and minuses. So what you do is write the numbers as blank numbers and set it equal to the middle number. In the case, the middle number is a positive 1. And your job is to put minuses, pluses, minus and pluses, whatever you want to make this a true statement. Hopefully it doesn't take a lot of thinking to know that positive 3 minus 2 will give you a positive 1. So those are your symbols, positive 3, negative 2. That is the fact form of number 6. It does get a little bit more thinking involved if there is a leading coefficient other than 1. So then, again, in this instance here, I know whatever I put here and here has to multiply to 2k squared. In this case, it's going to be 2k and k. 2 times 1 is 2. But same concept, whatever numbers I put into here has to multiply to 18. So let's pairwise factor 18. 1 and 18, 2 and 9, 3 and 6, and I think that's it. The middle symbol is a plus, so I think of add. But do know something. Because I know for a fact the leading term here has to be a 2, do know that whatever you put into this position will get multiplied by 2. So what I'm thinking is, what pair such that, ST is such that, when I multiply one of them by 2 and then add, gives me a 13, because the 13 is the middle number. So again, this just takes mental math. There's no trick about it. You just got to keep trying until you find it right. So let's try the first pair, 1 and 18. What if you multiply the 1 by 2? 1 times 2 is 2, plus 18 is 20. That's not 13. Flip it around. 2 times 18 is 36, plus 1 is 37. That can't be it. Try this pair. 2 times 2 is 4, plus 9 is 13. Hey, that's exactly what I want. Now notice we did 2 times 2, which tells me that the 2 has to go in this position, and the 9 has to go in that position. So let's write down the blank numbers. 9, and a 2 plus 2 is 4, and I want positive 13. That's what's in the middle. I hope this is not a hard question for everyone. I hope everyone knows that positive 9 plus positive 4 gives me a positive 13, so they're both positive. That is the factored form. Let me go ahead and rewrite it all cleaned up. So that's 2k plus 9, k plus 2. All right. Number 8, same thing, more factoring, but because the first term is a 4b squared, or the coefficient is 4, 4 actually has 2 possibilities. It could be 1 and 4 and 2 and 2. We don't know which one is which, so we have to cover all bases. It could be 1b and 4b, or it can be 2b and 2b. It literally is the same concept, except you have more guesswork to do. So I'm not going to go through this rundown. I'm not going through the whole thought process, but you guys can do it on your own. So it ends up being that the factored form is b plus 2 and 4b plus 7. Number 9, notice it's an x to the 4th. However, it follows the quadratic pattern. This exponent is twice as much as the middle exponent, and it ends in a constant, irregular number. So you can make this look like a quadratic by letting the variable u, or whatever letter you want, to equal the middle variable. In this case, it's x squared. That transforms the problem into u squared minus 4u minus 21, which hopefully we can factor pretty simply like normal. U and u, two numbers that multiplies to negative 21 and combines to negative 4, would be a negative 7 and a positive 3. The only thing we have to remember is that our original problem wasn't in terms of u, it was in terms of x's, so you have to go back and wherever you see a u, substitute in an x squared. So the factored form is x squared plus 3, x squared minus 7. Number 10 was factoring with 4 terms, and the idea is that when you're asked to factor 4 terms, more likely than not, it'll be factored by grouping. The way you do that is you have to look at the first 2 terms as its own set, and then the last 2 terms as its own set. And do notice I highlighted the this symbol here with the second highlight, because you got to include it. So I'd rewrite the problem as, in its own parentheses, 15m cubed plus 9m squared, close the parentheses. It's always a plus, and then go ahead and write the second half, including the symbol. So in this case, it's plus 40m plus 24. Then all you have to do is factor out the greatest common factor. In the first parentheses, I can factor out a 3m squared, leave me with 5m plus 3. In the second parentheses, we can pull out a 8, and what's left over is a 5m plus 3. Your goal when you're factoring by grouping is to get these parentheses to be the same, in which case they are. If they are the same, you can go ahead and factor him out. And then once you factor it out, you have to put your leftovers in its own separate parentheses. Clearly, I hope everyone can see that the leftovers are 3m squared plus 8. Right? So that's the factored form for number 10. Number 11 is a multiplication of rational expressions. Remember, I said in class, it's sort of ironic, when it comes to multiplying and dividing rational expressions, you actually don't multiply and divide. The name of the game is factor and cancel. Now this one was actually even easier. I didn't notice this at the beginning, but notice how this numerator is 100% the same as this denominator. I don't have to factor those guys. They immediately wipe out themselves. So all that's left is 1 over 4p cubed plus 12p squared times 4p cubed minus 12p squared over 1. And then it's these guys here that I would go ahead and factor and see if I could cancel anything. So let's go ahead and factor those guys. That's 1 over, it's two terms, it's not a trinomial, so it's just regular GCF. I can pull out a 4p squared, leaving behind a p plus 3. And then in the numerator, I can pull out a 4p squared again, leaving behind a p minus 3. Hopefully everyone can see that the 4p squares will cancel out. And then all that's left over is a p minus 3 on top and a p plus 3 on the bottom. So multiplying and dividing rational expressions, all it is factor and cancel. For number 12, which is a division example, you don't want to factor and cancel until it's a multiplication problem. So you have to remember that when it comes to multiplying by fraction, keep the first fraction the same, change the division to multiplication, and take the reciprocal of the divisor. So I'm going to rewrite this problem as the first fraction stays the same, change it to a multiplication problem, and take the reciprocal of the second fraction. Then you go ahead and factor like crazy here. So this guy here, I can pull out a 2. So that's 5k squared plus k minus 4. So that's this guy here. Over here, I can pull out a 2 as well. So that's 2 times 2k squared minus 3k minus 5 times this guy here. It's a binomial. There's only 2 pieces, so it's GCF. I can pull out a 4k squared, leave behind a 2k minus 5, and then down here I can pull out a 4, leaving behind a 5k minus 4. I still have trinomials, these guys here. So what I can go ahead and my next step is to factor those guys. Notice anything I do not highlight, I'm just going to copy down. Did not highlight the 2, so bring them down. I'm going to factorize this trinomial, 5k and k, and again it's just practice factoring, so I'm not going to spend the time explaining it. We should be a little bit better at it by now. So that's going to be a plus 1 over here and a minus 4 there. I'm going to factor the trinomial in the denominator, 2k and k. So let's see, 5 and 1, so it's going to be a plus 1 over here and a minus 5 over here. And then the second fraction, I didn't highlight anything, so I'm just going to copy everything down. Now it's time to cancel like crazy. I can cancel out the 2's. I can cancel out the 4's. I can cancel out the 5k minus 4's. I can cancel out the k plus 1s, remember the I colors. I can cancel out the 2k minus 5, and that's it. So all this work, what's the only thing that's left over is the k squared. That's pretty cool. That giant problem simplifies to a k squared. Number 13, simplifying a compound fractions. There are a couple of ways to do this. For this solution, I'm only going to show the way I like, which is clearing a fraction. So the first thing I need to do is find the LCD. To find an LCD of a complex fraction, you have to look at the inner denominators. What I mean is, you have to look at the smaller denominators within the problem, which I've highlighted. To find the LCD, you go ahead and write the denominators in stacked form, so just on top of each other, and factorize them if you can. I can't factorize m plus 1, so it stays as m plus 1. Do notice I use parentheses because the m plus 1 is the entire denominator. Can't factor the m. I can't factor the m plus 1. I can't factor the m plus 1. So once you've listed the denominators and try to factor them if you can, the LCD will consist of common factors when you look vertically, when you look up and down. So you look up and down the list and ask yourself, are there factors that repeat? Are there factors that appear in multiple rows? And I hope everyone can see that the m plus 1 is in common. And once you've factored all the common factors, then you have to look for any factor that wasn't circled or used. And hopefully everyone can see that you have this lonely m that's not used. So that's your LCD, m times m plus 1. What you're going to do then is multiply every single fraction by the LCD. I'm going to rewrite the problem just to give myself a lot of room. So 2 over m plus 1, leave a space, a big space, plus 3 over m over m squared over m plus 1, leave yourself a big space, plus 4 over m plus 1. So all I did was I copied down the problem, and what I'm going to do is for every single part of the problem, multiply by the LCD, m plus 1, m plus 1, m plus 1, m plus 1. And the idea is, since we're using the least common denominator, all of the denominators should cancel out. Top left corner, the m plus 1s are gone. Top right, the m's are gone. Bottom left, m plus 1s are gone. Bottom right, m plus 1s are gone. And then all you have to do is just multiply what's left over. So what's left over in the top left is 2 times m, which is 2m, plus 3 times m plus 1, which is 3m plus 3, over in the denominator, you got m squared times m, which is m cubed, plus bottom right, 4 times m is 4m. All you have to do is combine like terms and factor. So we have 5m plus 3 over m cubed plus 4m. You could factor out an m from the denominator, but it doesn't cancel out with the numerator. So that is the simplified form. Find the LCD, clear the fraction, simplify. Number 14 was just a straight up linear equation, no fancy tricks. First thing I like to do is simplify the problem by breaking down the parentheses. So I'll just go ahead and distribute the negative 4, distribute the negative 8, give me negative 4x minus 8 equals negative 8x minus 24. And the idea is to get the x's on one side and the regular numbers on the other. So I'm going to do 2 steps at once. I'm going to add the 8x on both sides. And I'll go ahead and add this 8 on both sides. So that gives us 4x, these guys are gone, equals, these guys are gone, negative 16. Divide up the 4, x equals negative 4. Now, number 15 was an example of an absolute value equation. The idea is that you want to get the absolute value by itself. So you want to get those bars by itself. Hopefully it's very obvious to see that we need to get rid of the minus 10 and we need to get rid of the 6. So the first thing we're going to do is add 10 to both sides. Give me 6 absolute value, 1 minus 4m equals 126. Divide both sides by 6. You get absolute value of 1 minus 4m equals 21. Now the way we handle the absolute value is to use the definition. So recall that the definition of absolute value of anything, x in this case, That absolute value can give you the exact same thing out, or it can give you the opposite of what you put in out, depending on the sign of the input. Now, since our input contains a variable, we don't know if it's positive or negative. We have to cover both bases. So, by definition, this absolute value of x of 1 minus 4m could give me the exact same thing out, 1 minus 4m, which, according to the original equation, equals 21, so equal to 21. Or, by definition, this absolute value could equal the exact opposite of what I put into it, which at the same time equals 21. These are the two equations we're going to solve. So let's just go ahead and solve these two equations. On the left here, let's subtract 1. Negative 4m equals 20, and divide out the negative 4 gives you m equals negative 5. On the right here, you can go ahead and distribute the negative 1, or what I like to do is I like to divide out that negative just so that my steps become the same. So it's 1 minus 4m equals negative 21. Go ahead and subtract the 1. Negative 4m equals negative 22, and then divide out the negative 4. Gives you a positive 22 over 4, which is 11 over 2. Since this equation, here was our equation once we isolated the absolute value, it equaled a simple number. I mean, I should always check my answers, but in this case, I'm fairly confident in my answers because it was just a regular number. You only have to check your answers, really, if there was another variable on the other side. Number 16 was just a simple quadratic equation. I gave you a hint of solve it by factoring, but honestly, I didn't really care what method you use as long as you're correct. But the idea is to solve a quadratic equations that have x squares and, or in this case, a squares and regular a's, is to move everything onto one side. So we have to set up the problem first. Let's add 1 to both sides. And let's subtract the 6a squares on both sides because we want a 0 on one side here. So that gives me 7a squared plus 8a equals 0. Now normally we would have to factorize, using those two parentheses, but we don't have a quadratic trinomial. We have a binomial here, just two pieces. So it's just nothing fancy, just GCF, greatest common factor. And the only thing they have in common is an a. So now we can apply the zero product property. Once it's factorized and it equals 0, that's the key here. You go ahead and set each separate piece equal to 0. So the a equals 0 and the 7a plus 8 equals 0. Now there's nothing to solve here because the letter is already by itself. And the right equation is just a simple two-step equation. Subtract the 8, divide out the 7. A equals negative 8 sevenths. Right. Number 17 is an example of a rational equation. Again, lots of different methods to solve this. The method I like is clearing the fraction. So to clear the fraction, I need the LCD. So you have to look at all of the denominators. Go ahead and write them stacked together and factorize them. I can't factorize b minus 4, so it stays as b minus 4. Hopefully I can factorize the quadratic trinomial, and that's b minus 4, b minus 4. So the LCD equals, again, you have to look vertically. Do not look horizontally. That's bad. Look vertically. Do they have anything in common? They have a single b minus 4 in common. And then this guy is all by himself, so you got to put him down. So that's the LCD. I'm going to suggest to everyone to take the extra step. So this is a extra step. Not everyone does it, but I suggest you do it. Rewrite the problem. Put yourself some spaces in between each term. And write down the denominators in factored form. So instead of writing b squared minus 8b plus 16 over here, I'm going to write b minus 4, b minus 4. And then go ahead and multiply every single term by the LCD. So this guy gets times b minus 4, b plus 4, or excuse me, b minus 4, b minus 4. They're both minuses. B minus 4, b minus 4, b minus 4, b minus 4. separate the scratch work here. If we did things correctly, all the denominators should cancel out. So this 1b minus 4 cancels out in the middle. Both b minus 4s cancel out on the right-hand side. Unfortunately, nothing cancels out on the far left, so we're actually going to have to multiply that all the way through. So on this part here, just FOIL it out, which we know what it is. It was the original denominator. That's going to give me b squared minus 8b plus 16. In the middle, we just have a plus b minus 4. And then on the right-hand side, since the denominators cancel out, we have b squared plus b minus 12. Notice it gives us a regular equation that we can go ahead and solve. I'm going to clean this up a bit. I'm going to combine like terms on the left-hand side. So I have a minus 8b here and a positive b here I can combine. I have a regular 16 and a minus 4 I can combine. So on the left is b squared minus 7b plus 12 equals b squared plus b minus 12. I hope everyone can see that if we subtract the b squares, they're gone. So we have negative 7b plus 12 equals b minus 12. And then it becomes a regular linear equation. Get the variables on one side, get the numbers on the other. So let's see if we can do this in one step. Add 7b to both sides. Add 12 to the other side, giving us 24 equals 8b. Divide both sides by 8, you get b equals 3. But when it comes to rational equation, you always have to check your answers, and you have to check it against the denominator. We do not want the denominators to be 0. So the denominators in our original problems were b minus 4 and b minus 4, b minus 4. Do notice that the number 3 will not make any of these factors equal to 0, and that's good, that's safe. That means we keep this answer. Last but not least, a radical equation. So the idea is, just like with the absolute values, if your problem has any special symbols, you want to get the special symbol by itself first. In this particular instance, the radical is already by itself, so we can go ahead and get rid of it. The opposite of a square root is a square, so we're going to square both sides. Common mistake I saw, people doing this. Oh, I'm going to distribute the 2, r squared plus 1. This is bad. You cannot distribute the exponent because it's a binomial. There's a plus in there. So r plus 1 squared, you either know the pattern, or it's just r plus 1 times r plus 1, and you go ahead and FOIL it that way. That's r squared plus 2r plus 1. So back to original problem, the left-hand side is r squared plus 2r plus 1 equals, and then the right-hand side, the square and the square root cancels, giving you a 6r minus 2. Notice it's a quadratic equation. You have r squares with regular r's, so same technique. Bring everything onto one side, and then solve by factoring, quadratic formula, containing the square, what have you. So we're going to do 2 steps, subtract the 6r, and then we're going to go ahead and add the 2 to both sides. R squared minus 4r plus 3 equals 0. Fortunately, this is factorable. R minus 3, r minus 1. If you set each of them separately equal to 0, you're going to get r equals 3, r equals 1. But when it comes to radical equations, if there are variables on both sides in the original problem, you must check your answers because you may get extreme solutions. So to check r equals 3, just plug into the original equation before you squared it. So 3 plus 1 equals question mark, the square root of 6 times 3 minus 2, and then you just do math. 4 equals question mark. That's 18 minus 2 is 16, and of course 4 does equal 4. That's good. To check, so I'll circle this guy. To check x equals 1, get 1 plus 1 equals question mark, the square root of 6 times 1 minus 2, just plugging it in. To the original problem, you get 2 equals question mark, the square root of 4. 2 does equal 2. That's good. So both of them are our answers.